Photoelectric Effect 光電效應 Planck proposed that light consists of particle nature called photons 光子 The energy of a photon E equal to hf equal to hc over lambda, where h is the Planck constant equal to 6.63 times 10 to the power negative 34 joules per second. F is the frequency of the light, lambda is the wavelength of light, and lambda equal to c over f, or we say f equal to c over lambda, where c is the speed of light in vacuum. Second, each photon travels at the speed of light. Example 1. Part A. The energy of the photons in joules equal to the energy of the photon in eV times 1.6 times 10 to the power negative 19, because we know that 1 eV equal to 1.6 times 10 to the power negative 19 joules. Therefore, the energy of the photons equal to 2.59 times 10 to the power negative 19 joules. Part B. Because E equal to hf, we have frequency of the photon equal to E over h equal to 2.59 times 10 to the power negative 19 over 6.63 times 10 to the power negative 34, which is equal to 3.91 times 10 to the power 14 pulse. How many photons are emitted from a monochromatic light source per second? If we let P to be the power of the light source, F be the frequency of the light, and N is the number of photons emitted per second, then we have power P equal to N hf, where hf is the energy of one photon, and nhf is the total photon energy emitted per second, which is the power of the light source. Example 2. By the equation P equal to nhf equal to nhc over lambda, substitute P equal to 30, H is 6.63 times 10 to the power negative 34, C is 3 times 10 to the power 8, lambda equal to 6.6 times 10 to the power negative 7. We have the number of photons emitted in 1 second, N, equal to 9.95 times 10 to the power 19. How are the intensity of light I and the power of light P related? We know that the unit of intensity is watt per meter square and the unit of power P is watt. If the light is perpendicular to the surface of area A, then we have power of light falling on the surface area A equal to intensity of light I times the surface area A. However, if the light acts in a direction with angle theta to the normal on the surface of area A, then we have power of light on the surface equal to I cosine theta times A. Example 3. The power of light in this case is equal to IA equal to 60 times 4 equal to 240 watts. And the power of light on the surface is P pi equal to I cosine theta times A equal to 60 times cosine 30 degree times 4, which is equal to 208 watts. What is photoelectric effect? 光電效應. When a beam of light carrying photons with sufficient high frequency F, that is sufficient high energy photons, is incident on a metal, electrons in the metals are ejected or emitted. The ejected electrons are called photoelectrons. This phenomenon is called photoelectric effect. Notice that the collision between photons and electrons in a metal is a one-to-one collision, and the outcome is either case 1 or case 2 during the collision. Case 1. If the frequency of the light, or we say the energy of the photon, is high enough, the electrons will absorb the photon and emit it from the metal. However, in case 2, if the frequency of the light or the energy of the photon is small, the electrons in the metal will not absorb the photons and never be emitted or ejected. The definition of work function of a metal phi. Work function phi of a metal is defined as the minimum energy needed to eject an electron from a metal. Note that the electrons on the metal surface are the easier to be ejected than those inside the metal. Therefore, work function refers to the electrons on the metal surface. Also, work function of a metal has unit in eV. Definition of first whole frequency. First whole frequency, F0, is the minimum frequency of light that can emit electrons from the metal. Note that the energy of a photon at first whole frequency F0 is E equal to hF0. Also, the energy of a photon at first whole frequency is equal to the work function of the metal, that is, HF naught equal to phi. It should be noted that when frequency of the light is larger or equal to the threshold frequency, photoelectrons are emitted. However, if the frequency of the light is smaller than the threshold frequency, no photoelectrons will be emitted. Example 4, Part A. The minimum energy of photons that can produce photoelectron is E equal to phi equal to 1.85 eV. For Part B, since the minimum energy E equal to HF naught equal to phi, which is 1.85 eV, equal to 1.85 times 1.6 times 10 to the power negative 19 joules. We have minimum frequency equal to 1.85 times 1.6 times 10 to the power negative 19 over Planck's constant, which is 6.63 times 10 to the power negative 34. Therefore, minimum frequency of light equal to 4.46 times 10 to the power 14 Hertz. Example 5. The energy of a photon equal to HF equal to Hc over lambda equal to 6.63 times 10 to the power negative 19 times 3 times 10 to the power 8 over 6.5 times 10 to the power negative 7 equal to 3.08 times 10 to the power negative 19 joules, which is equal to 3.06 times 10 to the power 19 over 1.6 times 10 to the power negative 19 eV, which is equal to 1.91 eV. Since the energy of each photon is smaller than the work function 4 eV, therefore we conclude that there are no photoelectron can be emitted. The experiment to demonstrate photoelectric effect. In the figure, we have D. Inside D, it is a vacuum chamber. Most part of the vacuum chamber is shielded from light by black coating. Light can only enter the chamber through the windows. C. Called cathode. It is a piece of metal used for emitting photoelectrons. A is called anode, which is the collector used for collecting photoelectrons. M is a mini emitter used for measuring photoelectric current I. V are variable DC voltage. Note that V is positive when the anode A is at a higher potential than C. This happens when S switch is connected to P. However, voltage V is negative when the anode A is at a lower potential than C. This happens when S is connected to N. The procedures for the experiments are: first, a monochromatic light of certain intensity falls into the metal surface through the chamber. Next, connect switch S to P and adjust the DC voltage and use the mini emitter to record the corresponding photoelectric current I. In this step, the voltage V at anode is positive. The result shows that when V is positive, the photoelectric current I is a constant value. Next, connect the switch S to N and adjust the DC voltage and record I. When S is connected to N, the voltage at the anode becomes negative. Experiment shows that when S is more and more negative, the photoelectric current drops. When V equal to negative Vs, the photoelectric current I becomes 0. Einstein used the photoelectric equations to explain the experimental result. He says that the energy of a photon HF equal to the minimum energy needed to eject a photoelectron plus the maximum kinetic energy of a photoelectron. In other words, the energy of a photon HF equal to the work function of the metal phi plus the maximum kinetic energy of a photoelectron. Hence, we have the equations HF equal to phi plus Ke maximum. Explanation of part 1 of the graph is photoelectrons are emitted with different kinetic energies. When V is positive, that is when the switch S is connected to P. Anode is at a higher potential than the cathode. Then, V larger than 0, the photoelectrons emitted by the metals are attracted by the anode. And reach the anode so that the photoelectric current is I, which is a constant value. Photoelectric currents I equal to number of electrons ejected per second times electronic charge. Also, I equal to number of photons incidents per second times electronic charge, since number of photons incidents equal to the number of electrons ejected. Therefore, we have I equal to NE, where N is the number of photons incidents per second. Since N is a constant value, therefore I is constant. Example 6. By using power P equal to N times HF equal to N times HC over lambda, we have P 100 equal to N times H is 6.63 times 10 to the power negative 34, C is 3 times 10 to the power 8, over wavelength is 500 nanometer is 10 to the power negative 9 meters. Therefore, number of photons incidents on the metal per second equal to the number of photoelectrons emitted per second, N is equal to 2.51 times 10 to the power 20. Therefore, the photoelectric currents I equal to NE, where N is equal to 1.6 times 10 to the power negative 19 coulombs. The result for the photoelectric currents I equal to 40.2 amperes. Explanation of parts 2 and part 3 of the graph. Photoelectrons are emitted with a range of kinetic energy. When V is negative, that is, when the switch S is connected to N. In this case, less energetic photoelectrons cannot reach the collector. Therefore, the currents will drop. When V equal to negative Vs, even the most energetic photoelectrons, that is, the photoelectron with maximum Ke, cannot reach the anode. Hence, low photoelectrons can reach the anode. In this case, the currents will drop to 0. At V equal to negative Vs, the maximum kinetic energy of the photoelectrons, it changes to electric potential energy with value equal to EVS, where Vs is called stopping potentials with unit in volt. Therefore, maximum Ke of photoelectrons equal to EVS. This equation is very important. Example 7. By Einstein's photoelectric equations, we have HF equal to work function phi plus Ke maximum. 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 over 420 times 10 to the power negative 9 equal to 2 times 1.6 times 10 to the power negative 19 plus Ke maximum. Therefore, the maximum Ke of photoelectron equal to 1.54 times 10 to the power negative 19 joules. Since Ke is half mv squared, we have the maximum speed of photoelectrons is equal to square root of 2 times 1.54 times 10 to the power negative 19 over mass of the electron, which is 9.1 times 10 to the power negative 31 kilogram, which is equal to 5.81 times 10 to the power 5 meter per second. Let's see the effects on the graph of photoelectric current I versus voltage V due to the changes of intensity and frequency of light. If light of intensity I pi and frequency f is shown on the metal, the graph of photoelectric current I against voltage V is shown in this diagram. Part A. If light of the same frequency f but greater intensity, the new intensity of light is greater than the original one. From photoelectric equations, we have Ke maximum equal to EVS, where Vs is the stopping potential. Also, the intensity of light is proportional to the number of photoelectrons emitted per second, n. For the same frequency of light, f, we have the same energy of photons. Therefore, we have the same maximum Ke of photoelectrons emitted. Also, we have the same stopping potential, Vs. If we have greater intensity of light, then we have greater number of photons incidence per second, n. So we have greater number of photoelectrons emit per second, also n. Therefore, we have greater photoelectric current, which is equal to Ne. As a result, the new graph would be greater current but the same Vs. It looks like this. Part B. Let's see what happened if now we have light of greater frequency but the same intensity. Compared with the original curve of light of frequency f and intensity I pi, if we use light of greater frequency, which is f pi larger than f, we have greater energy of photons, HF. Therefore, we have greater maximum Ke of photoelectrons emitted. Hence, we should have greater stopping potential Vs. However, if we use light of the same intensity I pi, the number of photons emitted per second n will be decreased. Therefore, the number of photoelectrons emitted per second by the metal n also decreases. In this case, the photoelectron produce the photoelectric currents I equal to Ne will also decrease. In this case, the case for light of greater frequency but the same intensity would be the result for photoelectric effects can only be explained by consider light as particle nature called photons. White photoelectric effect cannot be explained by treating light as wave nature. The reasons are that because the wave nature of light cannot explain the following experimental results. First, the stopping potential Vs only depends on the frequency of light, but it is independent of the light intensity. If light is wave, greater light intensity means we have greater light energy. So the electron will be ejected. Greater kinetic energy. Therefore, it should have greater stopping potential. However, this is not true in the experiment. Only when light exists as photons, the energy of each photon only depends on the frequency, but not on the intensity of light. The second result is that photoelectrons are emitted instantly, even the light intensity is weak. If light is wave, weak intensity means the energy of the light is weak. Therefore, the electrons in the metal needs time to absorb enough energy before ejected from the metal. That means we should have time delay. However, in the experiment, time delay is not found. This result can be explained by light exists as photons. The electrons will be emitted instantly when the frequency of light, f, is greater than the first whole frequency, which you have learned equal to f naught. That means f larger than f naught, electrons will be emitted instantly. The third experimental result is that there exists first whole frequency f naught. If light is wave, the energy absorbed by the electrons is continuously. Therefore, electrons always emit regardless of the frequency of the light. That means all the electrons in the metals will absorb the energy of the light continuously until it has sufficient energy to be emitted. However, this is not the fact in the experiment. The result is explained by consider light exists as photons. If the frequency of light is below threshold F smaller than F naught, the energy of a photon E equal to HF, which is smaller than the work function phi of the metal. Therefore, low photoelectrons will be emitted. You have learned that photoelectric equation is HF equal to phi plus maximum KE. Since work function phi equal to HF naught and maximum kinetic energy of photoelectron equal to EVS, therefore the photoelectric equation can be rewritten as HF equal to HF naught plus EVS. How to verify these equations? Experiment. First, we use the setup zone. In this case, we have the collectors is at a lower potential than the metal. Therefore, it is a negative potential. When monochromatic light of frequency F falls onto the metal M, photoelectrons are emitted to collector C. Photoelectric current I can be measured by the galvanometer. Adjust the voltage V to Vs, which is the stopping potential. The current becomes 0. The experiment is repeated with using another monochromatic light of different frequency F, and the corresponding stopping potential Vs is measured. By plotting the graph of stopping potential against frequency F, we obtain a straight line. From the equation HF equal to HF naught plus EVS, we have Vs equal to H over E times F minus F naught. From the graph, the slope equal to H over E, and the x-intercept will be equal to the first whole frequency F naught. If the metal is replaced by another one with greater work function phi, the first whole frequency F naught would increase because phi equal to HF naught. However, the slope of the graph H over E remain constant. Therefore, the new graph would be like this one. It's a straight line parallel to the previous one, but with a greater threshold frequency. Example 8. The slope of the graph equal to H over E equal to 4 times 10 to the power negative 15. Since electronic charge E is 1.6 times 10 to the power negative 19, therefore we have the Planck's constant equal to 6.4 times 10 to the power negative 34 joule second. Since the x-intercept is equal to threshold frequency, therefore the threshold frequency is equal to 6.2 times 10 to the power 14 Hz. Therefore, the work function phi equal to hf dot equal to 6.4 times 10 to the power negative 34 times 6.2 times 10 to the power 14, which is equal to 3.97 times 10 to the power negative 19 joules, or equal to 2.48 eV. That is 2.48 electron volt. Example 9. By HF equal to phi plus K.E. maximum equal to HF lot plus EVS. Substitute the frequency into F. And the stopping potentials into Vs. We have two equations. By solving the two equations, we can find the value of H and F lot. Bear in mind that Vs should be changed to units of joules. That is, if Vs is 0.95 eV, it should be changed to 0.95 times 1.6 times 10 to the power negative 19 joules.